Alright, so we are ready to talk about a very important rule for finding derivatives called the chain rule. And it basically deals with finding the derivative of a composition of two or more functions. I just want to remind you real quick, compositions, we reviewed a little bit with some of the prerequisite homework that you guys worked on. But a composition, right, looks like this. F circle G, maybe you've seen that notation before. All right, this means what? F of G of X. And so when we're looking at a function, we say this is a function like this is a composition of functions. This is not multiplication. This doesn't mean F of X times G of X. That is not what this is. So you've got to understand the difference in the notations here. All right, this is F of G of X. And so when we look at this function, we're thinking of some function g that we're starting with, right? We're plugging in some input x, some independent variable, right? A value in the domain of this function, right? And this function then will output, right? The dependent variable, we say g of x, right? G of x. G of x, the whole thing is a variable. G itself is a function, but x is a variable. G of x is a variable too. It's the dependent variable. It's the output of the function. So input x, output g of x. That's the idea. But now what we're going to do is we're going to take this variable now as an input to the function f. And the output is f of what? F of what we plugged in, f of g of x. So that's what we mean. So it's a composition. And sometimes we talk about these two functions in a composition, g as being the inner function in the composition. Right? It's kind of inside here, right? The inner function. It's inside, right? Being plugged into what this function f, which is what? That is the outer function. So that's just a quick review of compositions of functions. And so we've been using that already when we look, say, at the difference quotient, right? The difference quotient had this thing, f of what? X plus 3 or something like that, or f of x plus h or whatever in general. But x plus 3 is the function that we're calling g of x here. Right? That's the inner function. The outer function f is, well, whatever that function is, and we plug it in and we simplify the difference quotient. Right? So that's a composition there. And of course, all we're doing is when we see this input, we're replacing the independent variable, the function f, with that expression, and then simplifying. Okay, so that's composition of functions. And so how do we find the derivative of such a thing? Well, here's how we do it. If y is a differentiable function of u, so u here now we're going to let be equal to g of x. U itself is a function of x, right? U is the inner function, what we've been calling the inner function. And we just use this notation u to simplify things a little bit. U is a function of x, and then y is a function of u. So if y is a differentiable function of u and u is a differentiable function of x, then the composition that we can form, y equal f of g of x, right? G of x is the inner function, and f then is the outer function. Then that composition is a differentiable function of x. And here's how we find the derivative. This is the Leibniz notation. dy dx is equal to dy du times du dx. And this is wonderful notation because it kind of makes sense. Remember, these are not really fractions per se. They sort of indicate slope, right? Again, that's what they're exactly indicating, the slope of the tangent line to the function, y in this case. But, right, it's not really a fraction per se. But if we think about it, and sometimes it's convenient to think about that, right? Small change in y over small change in x. Then we can think about it as multiplying these two fractions, small change in y over small change of u. This is dy du, the derivative of y with respect to u, right? Y is a differentiable function of u, and so that derivative exists. And u is a differentiable function of x, so this derivative du dx exists. But if I were multiplying these fractions, then the du's we can kind of think of as kind of almost, right, canceling out here. And what are we left with? Dy dx. So it kind of makes sense. That kind of makes sense. In function notation, we have the derivative of the composition f of g of x. We take the derivative of the outer function f, and we evaluate it at the inner function. and then we multiply that by the derivative of the inner function. So this right here really corresponds to the dy du part. That part right there from the Leibniz notation. And the g prime of x is obviously what? Du dx. Okay. Now the proof of the theorem is outlined in the textbook. It's difficult to prove rigorously, a little more than what I want to get into. But you could look at that and see how it works. It does use the limit definition of the derivative, and there's some things that we need to know about, of course, with these functions being differentiable and then therefore continuous and so on and so forth. But we want to look at applying this. This is the toughest rule that we have in some ways, and when we introduce this rule, it seems like from here on out, 90% of the time we've got a chain rule at least a little bit in there. Okay, so again, as we talked about the inner and outer functions, that's a good way of thinking about it. The chain rule y prime is the derivative of the outer function, right? Evaluated at the inner times the derivative of the inner function. That's what we have right here. The derivative of the outer function evaluated at the inner times the derivative of the inner function. Okay, so we're going to use both notations, Leibniz and this prime notation, as we work through examples. Notice identifying the inner and outer functions is real important. I've given some examples here. Here we have a composition, and one way to interpret this is the inner function u is 3x plus 4, and that's plugged inside what? The outer function y equal u to the 6th. So if I just replace u right here with 3x plus 4, I will get the actual function, right? 3x plus 4 to the 6th. So I'm composing, right, is what we say. Plugging this function u inside this function, right? Here, the inner function would be u is what's under the radical here, and the outer function is y equals square root of u, right, where u is all this stuff. Or we can write square root of u is what? U to the 1/2 is the way we would do it. Here's another one, y equals 1 divided by x plus 5. Here I can let u be x plus 5, and then the outer function is just 1 over u, or what? U to the negative 1 power. Sine 2x, and again, we write sine of 2x, but really this is sine of 2x, right? So if I let u be 2x, the outer function y is sine of u. Here I have y equals e to the cosine x. Inner function this time is cosine x, and the outer function is y equal e to the u. So a little different type of composition. So we'll have compositions involving all sorts of functions, and we need to be able to recognize the inner and outer function in the process, recognize the composition. Okay, let's take a look at some examples then. Let's differentiate using the chain rule. So here, let's just recognize again the inner function. All right, inner, I'm going to let be u, and that's 3x plus 4, and therefore du dx is what? What's du dx? What's the derivative of u with respect to x? What's the derivative of the inner function with respect to x? It's just 3, right? That's easy. That's just a line of slope 3, right? Its derivative is 3. And then the outer function would be what? Y is what? U to the 6th power. Right? So if I plug this in here, u is 3x plus 4, I'll get the original function. What is the derivative of the outer function, y, with respect to u? Well, that's just a power rule, right? The derivative of u to the 6th would be what? 6u to the 5th. Right? They're both differentiable functions, as we stated with the chain rule. And now we can find dy dx. So here I'm going to let y equal the function f of x. And so I get dy dx is equal to dy du times du dx. There's the chain rule. That's the chain rule. And so dy du was what? 6u to the 5th times du dx, which was just 3. That gives me 3 times 6, 18u to the 5th. Right? 18u to the 5th. Of course, our derivative is in terms of u, but do we want the derivative to be in terms of u? No. The original function was in terms of x. I want the derivative to be in terms of x. But we know what u is in terms of x, right? U is equal to 3x plus 4. So I can come back in here now and say this is 3x plus 4 to the 5th power. And there is my derivative. Alternatively, we could use the prime notation and think about it this way. And this is the way I take the derivative using the chain rule a lot, is, okay, the inner function is 3x plus 4. I'm just going to sort of cover it up, right? And it's then raised to the 6th power. So the outer function is u to the 6th. So I'd say, how do I take the derivative of u to the 6th? Well, that's 6u to the 5th, where u is what I'm covering up here. So I'm going to say the derivative of the outer function is 6u to the 5th. And what is u? What goes in the parentheses? Well, now I can pull it out and say what? 3x plus 4. So that stays the same, right? And then times what? The derivative with respect to x of what's inside, right? There's the derivative of the inner function. That's the same as our du dx here, which of course we know is equal to 3. And now I've got 3 times 6, which gives me 18, 3x plus 4 to the 5th, the same result. So this is the chain rule, and it wouldn't be absolutely necessary in this case to use the chain rule, but the alternative is quite daunting, and that is you could expand 3x plus 4 to the 6th power, multiply 3x plus 4 times itself 6 times, expand that out, and then take the derivative of each term. Okay, that's a daunting task. Not too bad. But imagine if it was 3x plus 4 to the 600 power. You would not want to expand that out. It would take you forever. But we can use the chain rule to easily do that, right? If this was 600, this would be u to the 600 power, and the derivative of u to the 600 is easy, 600u to the 599 power. And we can plug all that in, and we would have a result relatively easy in comparison. Let's look at another case. All right. This function now is the cube root. This is a cube root. Be real careful. I don't know if you can see that cube root of all this stuff. So I'm going to rewrite this as 3x squared plus 7x plus 5 to what power? To the 1/3 power. And now I'm going to use the chain rule. And I'm going to do it the way I did the second way for the previous example. And that is, I'm going to cover up, right, what's in here. That's the inner function, 3x squared plus 7x plus 5, right? And it's inside what? U to the 1/3 power. U to the 1/3 power. So the outer function is u to the 1/3. What's the derivative of the outer function? That's 1/3. U, subtract 1 from 1/3, I get negative 2/3, right? And what is u, right? U is 3x squared plus 7x plus 5. Very important in here, you don't take the derivative in here. You multiply all this by the derivative, right? So with the derivative with respect to x of the inner function. And what is that? What is the derivative with respect to x of the inner function? Derivative of 3x squared, just power rule and constant multiple rule. Bring the 2 down. 3 times 2 is 6x. Derivative of 7x is 7. Derivative of 5 is 0. And there's our derivative. So there's our answer. Now, the original problem did not have any negative exponents. This has a negative exponent. So we can rewrite, right, this part right here is the same as 1 divided by all this stuff to what power? Positive 2/3 power, right? The reciprocal, right, is what the negative exponent means there. And so if I clean all this up, what's my final answer? I've got up top here 1, 1, 6x plus 7. Multiply those three together. 3 times this times 1. I get 3 times and there's my derivative. Okay. In this case, right, it's really necessary to use the chain rule. Unlike the previous example where we could have got by without using the chain rule. Here it's required, it's necessary. I can't really expand or simplify this original function in any way. All right, let's look at a few more. Now, the first two examples involved the outer function being a power rule, basically, to find the derivative of the outer function. This time, what's the difference? What's our inner function here? Inner function is x cubed times e to the x. What's the outer function? Y equal what? Sine of, say, u. And we'll let, I should have said u equal, just to talk about the two. So the inner function is u is x cubed e to the x. Outer function is y equal sine of u. So I plug this into this one, right, and I get the original function. So what is our derivative? Dy dx. It's going to be dy du times du dx. All right. Now, when we find dy du, that's pretty easy, right? What's dy du? What's the derivative of y equals sine of u? Derivative of sine is cosine. Right? Cosine of u, right? But I'm going to replace u with what? What is u equal to? Sine of u derivative is cosine u, but u is what? X cubed times e to the x. Right? Times now the derivative du dx. What is the derivative of the inner function? Well, what am I going to have to use to find the derivative of the inner function? I'm going to have to use the product rule. See that? And so you can begin to see how things become nested together. We've learned the product rule. We've been using it, right? X cubed times e to the x. I've got product. And so inside, if you will, the chain rule, right? We're performing chain rule. And in the process of doing the chain rule, we take the derivative of the inner function. And what do we end up with? A product rule inside the chain rule. So a lot of times we have these rules nested together, so to speak. So what is the derivative of x cubed e to the x by the product rule? I'll take the derivative of x cubed times e to the x plus x cubed times the derivative of e to the x. Derivative of x cubed is 3x squared. Derivative of e to the x is e to the x. And so we get 3x squared e to the x plus x cubed e to the x. Sorry, I'm kind of off the screen there. So that goes here. We're multiplying by du dx. Okay, and that's a result that we can write as the answer. Now, a lot of times what you'll see is this stuff here kind of will be pulled out in front as a coefficient in front of cosine. You can also factor out some things out of this. Notice you can factor out x cubed e to the x. Sorry, x squared e to the x, I should say. All right, which leaves me 3 plus x. And so you might see this written this way: x squared e to the x, 3 plus x, or x plus 3, times cosine of x cubed e to the x. Okay. So just keep in mind right now, finding the derivative, if you leave your answer like this, that's fine at this point. But just realize, you know, if you're checking your work, looking at answers in the textbook or somewhere else, a lot of times they've simplified. They might have even factored something, or you know, try and rewrite it in a little more compact manner. So, but both are correct at this point. Let's do one more. The derivative of y equals e, and this is kind of hard to see, 3t divided by 2t plus 1. 3t divided by 2t plus 1. So let me just emphasize that this is y equal e to the 3t divided by 2t plus 1. Okay, so what do we have? The inner function is u equal what? It's this exponent, right? We have to evaluate that exponent first before we know what power to raise the outer function, which is what? Y equal e to the u. Right? So once I figure out the exponent, I can plug it in and I can evaluate this function. Okay. So the outer function derivative is real easy, right? dy du is easy. What's the derivative of e to the u with respect to u? That's just e to the u. That's an easy one. Now, when I find du dt, what do I have to use here? What rule do I have to find the derivative of this function with respect to t? That's the quotient rule. It's the quotient rule. So remember how that works. We take the derivative of the top function times the bottom minus the top times the derivative of the bottom. All over the bottom function, all squared. And now the derivative of 3t is just 3. The derivative of 2t plus 1 is 2. Now I can, and I should, simplify the numerator. In other words, I can distribute this 3 over the 2t plus 1, and then see if I can, subtract here and see if I can combine like terms. So 3 times 2t is 6t. 3 times 1 is 3. Minus 3t times 2 is minus 6t. Now don't expand the 2t plus 1 squared, just leave that factored. No need to expand that out. But up top, what does that simplify down to? 6t minus 6t is 0. We just have 3 up top. So let's go back to the original question, which is what is the derivative here of the function y? Notice it's a function of t, so we're looking for dy dt. dy dt. And what is that going to be by the chain rule? That's dy du, derivative of the outer, evaluate at the inner, right? Times du dt, right? Not du dx, because t is the independent variable here, derivative of the inner function. And so dy du is e to the u, but we don't want our answer to be in terms of u. We want it to be in terms of what? T. And what is u? U is just 3t over 2t plus 1 times the derivative du dt, which we found here to be 3 over 2t plus 1 quantity squared. Okay. Now this might be written a little more compactly. It's kind of a strange looking answer, but 3 times e to the 3t divided by 2t plus 1 all over 2t plus 1 quantity squared. Okay. And we are going to get some strange looking results as we use the chain rule and some of these other rules, as these rules that we've developed together. And so just be aware of that, we're mainly testing that you understand and know how to apply this rule, and so we're going to compose functions together in strange ways to make sure you can do that. Okay, so we'll stop this video here. We'll continue with some more examples, and we'll talk about the so-called generalized rules for derivatives using this chain rule.